Okay, guys. As I said before, the aldehydes are coming from the oxidation of the primary alcohol, while the ketones are coming from the oxidation of, this is oxidation here, oxidation of secondary alcohol will lead to what? To ketones. Primary alcohol oxidation will lead to aldehyde. However, tertiary alcohol here, what we said about those, no reaction. So you have to know this. So we have, so the primary alcohol of this cyclomethanol, this is cyclo, it's a pentane, cyclobentyl methanol. So this, the name of this will be, you name this one here as substituents. So cyclopentane, cyclobentyl, pentane. This is cyclopentane. So group will be cyclobentyl, and this is one carbon. One carbon is methane, correct? Methanol. So this is the name of this compound, correct? So in order to have this one here, we can get a primary alcohol. That's just easy to visualize this, and we can do it the same way they put it here. So this is, now I have to have what? OH here, H here, and H here. So you can see this is secondary alcohol. You have one substituent, correct? Carbon is only one, and then this is like R, that's your R. R, CH2, this is CH2, and this is OH. So, and this is R. So this is coming from this alcohol, primary alcohol, you get this cyclopentyl methanol. Here we have a ketone. You will have to have the secondary one. The secondary alcohol will be looking the same way we have here. Instead of one OH. So now, and this is H here. So the carbon that carries out the OH is connected to two R's. So the rest of this is R, and the rest of this another R, for example. That's a secondary alcohol. Here you have only one R. Here you have two R's. Correct? So when you oxidize it, you get this ketone. That's not cycloquinone, but that's not quinone. Quinone is totally different. Quinone has two oxygens. Okay? And the quinone, the oxygen is within the ring. This one outside the ring. Okay, this is outside the ring. So this one will be cyclo, because you have a carbon connected, will be cyclopentane. This is cyclopentane, correct? The whole structure here. Cyclopentanol as an alcohol will be cyclopentanal. So this is cyclo, that's an alcohol, and the whole ring is part of the carbon connected, and the OH you cannot, I mean you can, but it does not have any effect. It's number one, cyclo, and it's cyclopentanol. And then when it goes there, will be the same thing, cyclopentane, the same thing. We are going from pentane, correct? We took the E out here, take the pentane E here out, and then you add O-N-E, pentanone, cyclopentanone. So that's secondary alcohol. Tertiary alcohol, there is no reaction. So let's move forward here. I want to just the way the PowerPoints are written is so comprehensive, and there's a lot of mechanism, and I don't want you to be entangled in this mechanism. It's very simple. I love the mechanism in the organic chemistry, advanced organic chemistry, when I was in Germany. So it's nice, but you are just, this is an introductory to organic chemistry. It's not really per se. When you go for organic chemistry, 1 or 2, then you learn a lot of the different mechanisms. SN1, SN2, that's nucleify substitution 1, nucleify substitution 2, elimination, addition, all type of mechanism, you learn it there. But for the time being, I am not really pushing you, and even the final exam will never ask you about those mechanisms. Unless you are going for a higher chemistry and you are pre-med or pre-dentistry or pre-pharmacy, then you have to take organic 1 and organic 2. But for nursing, just enough for us without mechanism. The mechanism is very nice. It gives you the clear picture about which one is attacking which, so which atom is attacking which part of the molecule. Okay, so, and therefore you will see me skip a lot of stuff here when it comes to mechanism. I don't want you to be entangled in those mechanisms, and nobody will ask you those. So I'm not asking you about those mechanisms at all. So, and the final exam will not ask you. But if you go higher chemistry, then yes, you will be asked. You will be what? Oops, sorry. You will be asked about this. So now we have this type of reaction. That's, you have to know the product. Even the mechanism is too long. It's very simple. But you have to know the Friedel-Crafts alkylation and Friedel-Crafts acylation, both alkylation and acylation. So it has two parts. The idea is you cannot let benzene react, inreactive. The same thing with the phenol. Those benzene ring with the multiple groups. So this is with this delocalization of the triple three double bonds makes this very difficult to get hydrogen out. So this one here, for example, I'll write it here for you. This is a hydrogen, but I want to get this hydrogen out and let it react with another Cl here, correct? Let me take this one here out. So now I want to let this react together. This is the chlorine here, and I need the special catalyst. You can be asked about the catalyst, but not about the mechanism. The mechanism is a little bit more comprehensive. It's not difficult though. So it's very unique a reaction. That's aluminum. That's a catalyst you have to memorize. When it comes to Friedel-Crafts acylation or Friedel-Crafts alkylation. Alkylation, you add an alkyl group, correct? Acylation, you add an acetyl group. So what will happen here, you pull out with the help of this catalyst, the HCl. So the first thing here, you pull out HCl. And then what will happen? Then you will have, that's what will happen here. When you pull H here, usually without catalyst, you cannot pull this hydrogen. It's so tight with this delocalization of the triple bonds through the ring, make it difficult to pull out this hydrogen. So you pull this one out, and then guess what you get? You get this double bond, correct? And so you get something like this, and this is benzophenone. It has an IUPAC name. It's called benzophenone. So can you see that? Can you see that? We pull this one out. Again, you are not worried about the mechanism. We are not worried about anything. We are worried about Friedel-Crafts alkylation is used to pull out the hydrogen from benzene, which is very, very impossible in normal condition without catalyst, special catalyst called aluminum chloride, and this reaction called Friedel-Crafts alkylation if we are introducing alkyl group, or acylation if we bring an acetyl group. So what will happen here, we are producing then pulling out HCl, whatever the hydrogen out of the first benzene, connect the whole rest of the molecule into the other benzene. So that's a benzophenone reaction. Now how about this one here? What we are producing? Can somebody start helping me here, please?
So what did you ask?
What we are getting here, what the question here? Here.
Well, we're going to get HCl and
Okay. So let's look at this. We said this is, let's put it this way. Let me have green. Green color is good. So this is my benzene ring, and this is the hydrogen here, correct? Are you following me here? Friedel-Crafts alkylation, acylation use compound that has halogens inside. So then plus, it has a chlorine here, so I'll have to put as HCl, correct? And then C double bond CH3, correct? Now, pulling this one together, what I'm getting? I'm getting the ring is out, correct? Now I'm introducing what? I'm introducing this group here, correct? So C double bond CH3, of course, plus what? Plus HCl. So we have taken this one here, and this is the common name of this methyl phenyl ketone. So this is the common name of this will be methyl, correct? And then the benzene ring is a phenyl, and this is a keto group in the carbonyl group. Is a keto group, so will be ketone. So ketone. Always remember to have this, the functional group, the common name ends up with the same functional group: aldehyde, ketone, carboxylic acid, whatever the functional group, alcohol, whatever. Now, we can name, this is the only name we can name it, so we can think about having having this one here. This is 2 carbons, and the phenyl group is cannot be as a substituent, so will be 2 if you call ethanol, but that's you know, will be like 1 phenyl, one phenyl ethanol, 1 phenyl ethanol. That can be, but it's not really used. So you'll see those type of reaction yielding a lot of common name rather than IUPAC name, correct? So this is 2 carbon free. You treat this one here as substituent. So this is ethanol, from ethane, 2 carbons. This is ethanol, 2 ethanol, correct? If it's not a ring, then we can say that's a propanol, correct? Are you following me here? So if it's we have something looking like this: CH3 double bond CH2, and then here we have a phenyl ring. Then that would be what? That's a propanol, and 1 phenyl propanol. Are you following me here? But since we don't have, this is a carbon here, 1, 2, 3 carbons, and the carbonyl group is the keto group is the second one. So and 3 carbons, that's propane, take the out, propanone, and the phenyl group in the first carbon. So this is 1 phenyl propanol. But here we have only 2 free. You have to have In order to name aldehyde or ketone or alcohol or any of those carboxylic acid, you have to have a free carbons. It's not connected, it's not part of a ring. If it's part of the ring, most of the time is said to be what? It's a group as a phenol. It's a substituent as a phenol. So any question about this? I think we covered this one here. Let's go further here, guys. Now, sometimes dehydration of the triple bond will introduce for us what? Introduce for us the ketone itself. So here it is. Look at this. You have octine. Octine means you have 8 what? Octine. You have 8 carbons, and double bond is connected at the first one, not somewhere in the middle. So you have 8, 1, 2, 3, 4, 5, 6, 7, 8, and then number 1, this one here, and we are going all the way this way here to 8, correct? So the number 1 has the triple bond. Are you following me here? So the number 1 has a triple bond. That's an H because it has 4 bonding. So number 1, so that's an octine, 1 octine. You have to specify where is the triple bond, because it can be in the middle, it can be anywhere, correct? Anywhere. So it's at number 1. So then I can oxidize this, correct? I can oxidize this, and you can see, you can make out of this an octanone. Now, remember that all the time. Ketones cannot be at the first carbon. Aldehyde always at the first carbon. So if I have an aldehyde here, whatever 4, 5, 6, 7, 8, aldehyde always will be number 1, 8. So always at carbon 1. But the ketone cannot be oxidized as carbon 1. Are you following me here? Cannot. This is always carbon 1. That's an aldehyde. So this is, when I oxidize this, I'm expecting to get ketone at carbon what? 2. This one here, not the first. The first I will make out of this an aldehyde. Yes.
Are you saying that because secondary alcohol always oxidizes ketone? Is that just?
That's correct. That's all is interconnected. Yes, that's all is interconnected. So you are producing then here. The first one you cannot, because you will make an aldehyde out of it. So therefore you can make here the second one, the second carbon. And this is the first carbon. Then 2, 3, 4, 5, 6, 7, 8 from here. This is 8. Now you have, will be 2 octanone. 2 octanone. So you are producing what? An octanone, but where is the keto group? Is number 2. It cannot be number 1. Ketone will be always number 2. Aldehydes always number 1. Correct, guys? Now let's ask ourselves here if we have next step here. It's asking this type of flour here gives you 2-heptanone, oil of cloves. So how you write the reaction of this? Well, this one here, heptanone, is coming. It can produce from alkyne, correct? So what I'm going to do here, look what I'm doing here. I'm carbon copy this, copy here. I'm going. It's the same thing, the reaction I did here, paste. Let me see. I did not copy. Copy. So I'm pasting this one here, the same thing. And instead of having, I need heptanone, but we produce what? Octanone, correct? and that's we said it's an octanone. So what I will do, somebody will help me with this? So what should I do here with this reaction?
You have to
Instead of the 5, I have to put what? 4. So how many now we have? 7, correct? That will be, if I put instead of 5, that will be 1 heptane. Heptane, take the octane, heptane. So then, the same thing, it can be the first one. The second one will be, take this 5 out, put 4. That will be 2 heptanone. Heptane, O-N-E. The same thing we did. So just take 1 carbon down. Okay, guys, so that's a tab, another tab of reaction you can see. Again, you have my permission here as I'm recording here to have, to have everything ready and to use everything available to us, an open book, quizzes and exams. However, the usage of a cell phone is not allowed. Sometimes randomly I check, they will give me a lot of red flags because you are putting your eyes back and forth, back and forth. That's a violation with the software, but I just don't care about this. I gave you the permission to look to material, to search material, but the main thing, I don't want to hear any cell phone because it picks up all the voices surrounding you. Everything is so sensitive. Your laptop is really like it's really spying on you, and all the voices inside, I can't tell if there is a cell phone used or not. But anyway, so you have my permission to use anything you like. You can literally bring all the library in front of you here and put the whole library and put it in front of you. So that's fine, I don't mind. But the main thing, no cell phones. No cell phones. So this is aldehyde and ketones in nature. What did I tell you about the aldehyde and ketones in nature? Anything smelling, very nice. Not bad though. Not bad. Anything smelling very nice. Strawberry, pears, apples, oranges. All those, although they have some of them even carboxylic acid, but they have an aldehyde and ketones. Are you following me here? Anything smells very good from the fruits, especially the fruits, those they have aldehydes and ketones, and some veggies as well. So like vanilla is considered not a fruit, that's part of the veggies. Cinnamon, part of the veggies. They have distinct smell, correct? So vanilla, so all those here, I'm not going anywhere. But even camphor smells a little bit, stingy a little bit, but still not smelling like mercaptane, like smelling like skunk attacking people. Skunk is putting a lot of mercaptane out of its body to defend itself. Somebody wants to attack a skunk, the first thing it will do, it will just shoot the person or shoot the animal wants to prey on it with a lot of mercaptane, and the whatever animal is predators like lions, tigers, whatever, they will run away from the bad smell. So, but that's not the case of aldehydes and ketones. They smell very nice. Anything in nature, it smells, even the flowers, roses, they smell very nice, correct? So they have to have, your intuition will tell you, they have to have aldehydes and ketones, because that good smell always aldehydes and ketones. So here, I want you just to look at this, all this oil of almonds, smell of almonds, they smell. So cinnamon, vanilla, all this good stuff between fruits and veggies, good smelling, those are typical for aldehydes and ketones. Again, you can print anything you want. You can print the whole PowerPoints if you want to. Whatever you want to do it. So don't hesitate, okay? And the quiz is due this coming Sunday midnight. So you have 4 days, including this day. So you have plenty of time to study. So let's take an example here. Carbonyl group structure. This is we call it a mechanism of like a resonance. Resonance means sometimes the double bond changing. So that's what we call resonance, is delocation of the double bond, correct? So the carbonyl group can have this structure, a general structure, but it can have a polarized type of structure. Polarized means plus minus, partial plus, partial minus. So positive or partially positive, with delta means partially positive, partially negative. So what's happened is it opens up one of its ring, and then you will have it something looking like this. If one of the double bond will opens up, and it's a double arrow here, double arrow. It goes this way, it goes this way. This type of, we call it resonance, because the delocation of the double bond is always called resonance, okay? And the same thing with the Benzene ring, correct? The double bond is changing its location. That's we call it resonance, because it's moving around. So, and they tell you that the carbonyl group has hybridization of sp2 hybridization. If it's sp2, then it has to have 120 degrees, correct? So here it is, 102 degrees in carbon, so 102 degrees, and here's, for example, RR, if that's a ketone. So 120 degrees hybridization sp2, and the distance between carbon and oxygen is 1.24 angstrom. This single bond, and you have a double bond. The double bond can be delocalized, can be moved around, okay, as you have seen here. Now, the only thing here, for the geometry here, the shape of this molecule, it's not saying this, but the geometry is trigonal planar. Anytime I have SB 130, this information, the shape will be what? Trigonal planar, correct? So they are really flat. Trigonal planar means it's a flat plane. It's a flat, and it's a triangle flat, correct? So that's information about the carbonyl group. That's the hybridization here. Okay, sigma and pi, sigma between carbon and oxygen, and then the pi will come from the unpaired. Oxygen has available one p orbital. The carbon will have one, so they will make a sigma, the double bond. Okay, so that's sp. What's the physical properties of aldehydes and ketones? Well, aldehydes and ketones in general, they are polar. That's, we have to know they are polar. So they are polar. So this is the main thing, is they are polar. The idea of polarities comes from the oxygen, not the carbon. Carbon is less electronegative, so the polarities come from what? From carbon is more electronegative. Carbon electronegativity in the table is 2.1. This is 3.5. So you can see the electronegativity of oxygen is too large. So those electrons here will be always pulled out towards the oxygen. So that will utilize the polarity of the carbonyl group. So, however, this is a limitation, because they don't form among themselves hydrogen bond, but they can do hydrogen bond with H2O. If I have an H2O here H2O, for example, so the oxygen with the hydrogen. We said hydrogen bond. What did it say about hydrogen bond? A hydrogen bond, it has to meet two conditions. The bond has to meet two conditions. One, the presence of hydrogen in one of the molecules, correct? Second, the second molecule can have oxygen, nitrogen, or fluorine, those three elements in the second one. Here, in this case, we have oxygen. So we can have fluorine or oxygen, correct, and nitrogen. So each of those three will utilize hydrogen bond with the assumption that the other molecule has hydrogen. So H2O provide the hydrogen, and the carbonyl group the oxygen. Here we have hydrogen bond. So they are really making hydrogen bond with H2O. However, they can't make hydrogen among themselves. Are you following me here? So among themselves they can't. So this is oxygen and then R, whatever. So they can't make. You have to have the second one. The second molecule has to have free hydrogen. So, and H2O has a free hydrogen. It can be bound to one of those three atoms to make hydrogen bond. So that's about the hydrogen bonding. So since they are polar, so we are expecting their why we are talking about the hydrogen bonding, we are talking about hydrogen bonding because it's the more hydrogen bonds you have, the higher the boiling point, the higher the melting point. Both physical properties will be higher. Are you following me here? So you will see that's the aldehydes, they have higher melting point than, ketones and aldehydes. They have higher boiling points and melting points compared with the hydrocarbons, correct? But they are less than what the alcohol. Alcohol, they have more hydrogen bonding available to them. You can see here, that's alcohol here. So you have this can be bound to hydrogen bonding. This can be bound to hydrogen bonding. So alcohols, they have higher boiling point and higher amount of, higher boiling point, higher melting point, because they have higher amount of hydrogen bonding among themselves. And if they are soluble in H2O, so they will be soluble. Now, the ketones, smaller ketones and aldehydes, they are soluble in H2O because they are polar, correct? However, if you go then higher ketones and higher aldehydes, you can expect they are not soluble. Are you following me here? So when you eat the apple itself has aldehyde and ketones, but the aldehyde and ketones is very, very large. So you need that some enzyme will help you to digest this apple. But it's polar, it's soluble in H2O. When it's cut in small pieces, then the H2O will come and dissolve it. Are you following me here? So hydrogen bond is always helping us to determine the physical properties of the compounds. The higher the hydrogen bonding number of bondings, the higher the boiling point, the higher the melting point, correct? So the aldehydes and ketones are less than the alcohols. And you will see the carboxylic acid, they have more oxygens to that. So carboxylic acid is more polar than alcohol, than aldehyde and ketones, correct? Because they have more available oxygen into them. So carboxylic acid will come to cover them. This is carboxylic acid function. For example, whatever this is CH2, CH. So this is carboxylic acid. It has this and it has this. This one here, a hydrogen can make hydrogen bond. This can make hydrogen bond. This one can make hydrogen bond. So you can see this carboxylic acid melting point and then boiling point is higher than alcohol, higher than aldehyde and ketones because they can have more hydrogen bonding, correct? So that's regarding the physical properties. And of course, don't forget the physical property of the smell. They have distinct smell of fruits and veggies. Now, I want you to look at this. You tell me which one. So arrange benzaldehyde, benzyl alcohol, and paraxylene. So let me paraxylene here. the paraxylene will be looking like this. Okay, so, and the benzyl alcohol is that's your benzyl alcohol. And benzaldehyde so which one, according to you, will have higher melting point? Ranking them by the number now. Don't worry about this. We are doing this, but in numbers. So, which one? This one here, or this one here, or this one here?
Yeah.
Is this polar? This is not polar. Where is the polarity will come from? That's nothing. That's like an alkane. That's an aromatic, but it's like an alkane. It's not polar. This is polar? Yes. Polar. It has OH. Correct? This is polar? Yes. It has carbonyl group there. Now, which one will be higher in boiling point compare what we said about the alcohol? Which one will make more hydrogen? So this is number 3. So we know that's number 3. This is not polar. There's no carbonyl group. There's no OH group. No nothing. So it's just like an alkane, alkynes and alkenes. So that's number 3. That's the lowest one in boiling point or melting point as such. So we said an alcohol will have hydrogen bonding. They can bond among themselves, correct? If you have 2 molecules of this, you can connect themselves to hydrogen bonding with this self, but with this one here, they are not. You don't have a free hydrogen carbon. Here you have a free. See here, you have a free. So this is number 1. This is number 2. Remember always, alcohol, number 1, correct? Number 2 will be your aldehyde and ketones. Number 3, alkanes. But then when we have carboxylic acid, number 1 will take over. Then the alcohol, then the ketones and aldehyde, then alkanes, alkenes, alkynes, and aromatic. This is an aromatic, so this is the least. It's non-polar. It's not polar. So this is number 1. This is number 2. This is number 3. Why? This one has more hydrogen bonding with itself. The aldehyde and ketones, they cannot make hydrogen bonding with themselves. They are soluble in H2O, yes. If their molecule is smaller structure, but if you have huge, large ketones and aldehyde, they are not soluble. Okay, so that should give us at least. Remember always, alcohol until now, when we come to carboxylic acid, will be number 1 in hydrogen bonding, followed by alcohol, number 2, followed by aldehyde and ketones, number 3, and then alkanes, alkenes, alkynes, aromatics. Those are the last one because they are not polar anyway, so they are not polar. Imagine that the gasoline you put inside your car is polar. Bless you. So imagine that's your gasoline inside. What will happen to the tank, the car tank, gas tank? Will be eaten up by the gasoline, correct? But that's not happened. You can keep the gasoline inside your tank for months, for years. Nothing will happen. But you cannot put an alcohol or very aggressive carboxylic acid in your car tank. That will be eaten up. It will not take years, maybe months. You'll see a lot of rust and all the liquids coming out of your tank to the ground. So that's the whole idea, is those are very aggressive. So now, we have something called hemiacetals or acetals, and sometimes called them hemiactals and actals. So hemiacetals and acetals coming from the fact that if you add an aldehyde or ketones to alcohol, you produce, so no mechanism. I'm not going through this mechanism. So here it is. When I add an alcohol, see, plus an aldehyde here, guys, plus an aldehyde, if you add them up, you get called hemiacetal, which is characterized by one OR group, correct, from the alcohol. The R is the same thing, and then the H of the alcohol will come and make one OH. Now, I can go further here, guys. So here it is. Can I make another one? Yes. I will add H plus and I will add another OR. So I will add what? I will add another OR plus, that's a catalyst, another alcohol. Here it is. Another RO, oops, sorry, ROH. So now I have started with, I have produced, here is my R prime, H, and this is RO at the beginning one. Oops, sorry. Let me put it this way here. This one here, another ROH. Catalyst always your H plus. The catalyst is H plus. So what I'm getting out of this, let's put it here. So I'm getting out of this reaction, this is the, again, it's reverse reaction, goes this way and it goes the other way. So I'm getting out of this minus H2O. I'm getting out of this, look, S, I mean carbon C, and then R prime, H here, and then here I have OR and an OR. That's called acetal. Okay, guys? So, adding to aldehyde and ketones, you can get, if you added one molecule of alcohol, one molecule of aldehyde, you get hemiacetal. If you added two molecules more, two molecules, you'll get what? Acetal. So, let's put this one here. So, one molecule of alcohol plus one molecule of aldehyde will yield something called hemi. Hemi means half. Hemiacetal. However, if you get two molecules of alcohol plus one molecule of aldehyde, what you get something called acetal. So, one molecule of alcohol gives you hemi means half. Hemi means half. Half acetal. If you get two molecules, you get what? Acetal. Hemi means, the word hemi means half. Means half. Okay, guys? So, About the mechanism, you can look into the mechanism. I'm not really after the mechanism here, so just look at it here. So no need to know how you can, nobody will ask you, but if you go higher chemistry, yes, you will be able to explain the mechanism behind this. So it's always, this is nucleophile first attacking the carbon. Remember, carbon is partially positive, and the oxygen of carbonyl group is partially negative. And then from there you start the attack of the nucleophile, correct? So, any question about this? One molecule of aldehyde to one molecule of alcohol gets hemiacetal, half of acetal. Two molecules of alcohol plus one molecule of aldehyde. So in each case you have one mole of this. This is always 1 mole. Oh, sorry. This is always what? 1 molecule of aldehyde. But the only thing is the amount of alcohol you add. If you add 2 molecules of this in excess, then you have this acetal. Now, as I said, I'm not asking you about this, how to do the mechanism. Here it is, that's a nucleophile. So you have the nucleophile oxygen from alcohol here, the nucleophile from alcohol here with this. The oxygen is called nucleophile. So that's the reason is giving the mechanism without telling you all the details of the mechanism. You have to know what is attacking what. So you have a nucleophile with excess of those lone pairs will come and attack the carbon. This is negative. Remember, there's still negative, partial negative, will attack the partially positive. So this is partial negative, will come and attack. So this one here will come and attack this carbon. And then we'll add up the ORH, correct? That's the whole thing is partially, this is partially positive, the hydrogen. So when you dissociate the alcohol, the dissociation of alcohol will be like this. So it's acting like a weak acid, RO, partially negative, plus the H, partially positive. It's not per se that's very strong ions, but you have a partial separation. So always this is OR, and this is H plus. So you will see then the attack here. The first alcohol will come at itself as OR on the carbon. Carbon here is partially positive. That's carbon. So it will be attacked by this, and then you get the hemiacetal, half acetal. Then you get the second alcohol will come as a nucleophile, will come and attack the carbon there, and then you get out of this, if you add, correct, if you add more alcohol, ROH, so it will start attacking, this one will be start attacked, the OH will be kicked out. So what's the difference between hemiacetal and acetal? Well, acetal, hemiacetal, here it is. General structure is C, 1 OR here, correct? And then you have H, and here can be any R, say R prime. So here it is. This is distinct 1 OR, and then you have here OH, correct? That's a hemiacetal. Now if I have full acetal, then I have to take, let me take this one here out, then I will have the full acetal will be looking like this, the general formula. So the C our RO, correct? That's from alcohol. R prime, H. Then you have this one here is converted to another because you add another OR, correct? So you get out of this another alcohol, correct? So you get here another OR. So it is. That's called here acetal, full acetal. So how many groups acetal has? Has this and has this. So acetal has 2 OR, no OH. The hemiacetal 1 OR plus 1 OH. So can you now see the difference? For me, that's very important to distinguish between them rather than go through all this mechanism. And you don't know even the nucleophile, you don't know all the expression of this mechanism. So, but that's what we have. So this is by itself, and this is unique by itself. So an acetal will have 2 ORs, no OH. The hemi, the half of it, will be 1 OR and 1 what? OH. See the difference? See the difference between those? 2 OR, no OH. Here you have 1 OR and 1 OH. See the difference? Everybody is following me here? That's what I wanted to learn. About the mechanism, forget about the mechanism. So, because you have to know what nucleophile is, what the carbocation, this is not a nucleophile. A nucleophile means you have a negative. With the help of lone pairs of this negative atom, they will be as nucleophile, partially negative, so it will attack the positively charged, partial positive atom there. So, but the difference is, it will ask you to distinguish between hemiacetal and acetal. You will be ready. The hemiacetal will have 1 OR, 1 OH. The full acetal will be 2 OR, no OH. Are you following? Good, excellent. That's what I want you to learn. Mechanism, all this mechanism here, for me, is not important because you are not going advanced organic chemistry. If you go for advanced organic chemistry, then you have to learn it. And then you have to learn all the definitions. What is nucleophile? What is elimination reaction? What is substitution reaction? What is addition reaction? So nucleophilic substitution. So that's not our case. So, but I want you to learn this, how to distinguish them. Okay? And every time you need for acetal 2 alcohols, and for hemi, half acetal is 1 alcohol. Okay, guys, so that's the mechanism of hemiacetal. As I said, I'm not to this, but it's always about nucleophile of the alcohol from oxygen will come and attack carbon, partially positive. You get OR of the alcohol will be added in, and the H of the alcohol will be kicked out, or it will be kicked out, and then you get OH there. That's a hemiacetal. But anyway, just concentrate yourself on the distinguish characteristic of both, correct? So in the presence of excess alcohol, you have hemiacetal react to form acetals. We said that. So you need two molecules of alcohol to produce the acetal, and that's the reaction here. So this is the second added alcohol, and this one already the first added alcohol. Okay, guys, so that's the difference here. Okay, so go further with this. We'll go for another tab is linear reaction. That's the mechanism of the acetal. Second one, you added to the first one one molecule, then you added the second molecule. As I said, I'm not up to this mechanism unless you go for higher chemistry, because you have to know all those definitions. Now, here's very interesting to know, just sometimes nature with this type of the, like if this one here, 5-hydroxypentanal, that's an aldehyde, correct? The 5-hydroxypentanal, sometimes it can form resonance, okay? It can form resonance in the sense it can what cleavage, it's H plus here, the H here, not H plus, but the partial positive proton, and then it can cleavage it out, and then here it is, this in out, it will come and take the nuclei of oxygen, partially negative, of the aldehyde group, and then it will what? It will form like a cyclic ring. Either it's linear, correct, aldehyde. So when you have this type of reaction, you make out of this aldehyde is an alcohol, correct? So you make what? An alcohol. This alcohol will be secondary alcohol, not primary, because it's connected to what? It's connected to two groups. This is a group here, R, and this is R. So this is secondary alcohol. So that's how, not every molecule will do it, but some molecules, they tend to have sort of resonance inside, and they can entangle themselves from linear structure to cyclic structure, correct? To cyclic structure. So this is like from aldehyde to what? To alcohol. So now what we call this one here from aldehyde to alcohol. So is it oxidation or reduction? Or reduction? What do you think?
You said aldehyde to alcohol?
Yes. That's a reduction. Correct. Thank you. So this is by all means is not oxidation. This is a reduction. Some compounds, they not that many, but some aldehyde, they tend to have internal rearrangement, and they reduce themselves by themselves. So they can reduce themselves by themselves. No intervention from outside. No intervention from outside. So they can cleavage the proton of the hydroxy group, correct? So remember, when it comes to naming, which you will take first priority? The functional group of the aldehyde and ketone, or the functional group of alcohol? Which one will take first priority? What do we name this one here? Towards the alcohol or towards the aldehyde and ketone? Correct. So the aldehyde and ketone naming or nomenclature will take first priority over the alcohol. Are you following me here? Over the alcohol. So the alcohol will be then named as substituent. So hydroxy, correct? As hydroxy. This hydroxy connected to carbon 5-hydroxy pentanal. And then the cleavage of this OH, the hydrogen or the protons out of the OH, that will be cleavage, and this will be then going to the oxygen, nuclei. Remember, oxygen is partially negative. Hydrogen or the proton is partially positive. So it cleavage itself and it produce secondary alcohol. This is an internal reduction by the molecule by itself without interference. So we did not add anything. Some molecules will do that. They don't feel that they are stable when they are in this type of, of arrangement as aldehyde, so they are more stable to be in the alcohol form, correct? So, and you have seen that, guys. Sometimes you put some type of fruit outside, not in the fridge, for a while. There is sometimes bacteria will act on this. There is some oxidation, combustion from the air. But sometimes, even if you have it in a closed container, but there is by itself for a long time, not freezing, but just a normal temperature per time, you'll see the smell of that fruit or veggie is a little bit changing. So you will see this internal reduction, oxidation had happened. So this is the reduction. But it can be sometimes internal oxidation. Are you following me here? So you'll see the smell of it is not the same like it was before. Yes?
Are you talking about fermentation?
No, fermentation is totally different. Fermentation, you have bacteria. Bacteria is introduced, and bacteria is causing this fermentation. Yeah, so if you have rice, if you have grapes, can you make an alcohol out of grapes? Yes, you can. But the problem is you don't drink it at home, because what will happen is you have to distill it, because there's a lot of other bad alcohols there, like methanol, isopropyl alcohol, whatever. Those are not drinkable alcohol. But anyway, so that's an example here, and you have here an example of this. Has the mechanism, how does the mechanism is, the oxygen is the nucleophile, the negative, partial negative will come and attack the carbon that carries out the H and the oxygen. So then it will, you connected them here, and then what will happen, then the ring will close up, and then you get the hydrogen out. So this one out, and then this one will come, then you get the ring. So this one out. So you get the ring. So, okay guys, so out means what does not mean out. Out goes out, and then it attacks it, the partially negative oxygen. So, okay, so out, and it goes in here. So you add a catalyst H+, but then you recover it. So here, just give you the idea of this type of setup here. That's called the hemiacetal. Well, how we can tell that's a hemiacetal is, hemiacetal, we have said that it has to have always one OR, one OH. That's to be hemiacetal. So this carbon here has one OH, correct? And it has OR, so O here, O, and the rest of the molecule is, the rest of the molecule is R. Correct? That's the rest of the molecule is R. So it has one OR and one OH. Okay, guys? So that's a hemiacetal carbon. Hemiacetal carbon. So it has to have one OH. It does have one OH. And then OR, you have an oxygen, and the rest of the molecule is R. So it will be OR. This is another example of making the same thing. Remember, we said one molecule of aldehyde to one molecule of alcohol makes hemiacetal, correct? Two molecules of alcohol with one molecule of aldehyde makes what? Acetal. The same thing here with this one here. You have ethylene glycol. Where we use ethylene glycol? Somebody will tell me. We talked about these guys. We talked about this. That's a coolant, correct? So antifreeze is or antifreeze or antifreeze. It's used as a coolant. You can't use H2O, especially in very hot areas. It will evaporate from your radiator. So you have to use a coolant that's just, it's not evaporating at boiling point at lower temperature. This one you need higher temperature to let it evaporate. So this is ethylene glycol, and you add a ketone to it. The same thing. That's an alcohol. Same one. This is 2 alcohol. This is what it is. How many alcohols we have here? 1 or 2? 2 alcohols, correct? And 1 ketone or aldehyde, 1 ketone, 1 molecule of ketone. Or if you want an aldehyde, 1 aldehyde will do it too. So you get, what is this? This is hemi or fully acetyl? Acetyl, correct. That's what we are looking for. Why? You have here, you have what? You have 2 alcohols. 2 alcohols, correct? So OR and what? Another OR. So that's an acetal. Okay, guys? That's an acetal. You have to recognize it as an acetal. So reaction summary. This is about the 1 alcohol first. You get the hemiacetal, then you add the second one, you get acetal. Okay, so here says benzaldehyde. You tell me, benzaldehydes look like this. And you have methanol out of this. So methanol is OH, CH3. So you'll get what? 1 molecule, correct? No, it said excess. Excess of it. So we'll take 2 of them. We're not interested in more than 2 excess. So excess, if that's it with least amount of methanol, then what will be then here? Somebody will tell me? Okay, perfect. OR here, this is my OR, correct, from alcohol. Another OR, that's OR here. 2 ORs, correct? And 1 hydrogen, and then just the rest is the pencil ring. Nothing new. Okay? 2 ORs, no OH. That will be acetal or hemiacetal? Acetal. This is acetal. Why? The keyword is that's in excess. If we are said with limited amount of methanol, then that will be what? Hemiacetal. Make sense, guys? Look at the keyword. Sometimes very important to pay attention for the keyword. So excess of it means we are interested in 2. We need just 2. But excess means a lot of it. But limited, just we'll assume that's just 1 molecule to 1 molecule of aldehyde or ketone. Okay, guys? So that's just an acetal. That's an acetal. Perfect. So the same thing here. The same thing we did. This is acetal or hemiacetal? OR, correct? Now, because this is reaction, we said reverse, correct? So if I take this one here, can I reverse it to the back where it's come from? Yes. This coming OR, no OH here, no OH. So can I take this one here and put it back in? Yes. That will be what? That will be an aldehyde. Correct? Plus methanol, 2 methanols. That's the reverse. That's the reverse, going from the acetal, complete acetal, to its original 2 molecules of alcohol, which is methanol, plus 1 molecule of aldehyde or ketone, depending what you are looking for, of aldehyde, correct? And this is an aldehyde. That's benzaldehyde. Okay, guys, so that's I want you to learn, but don't worry about having this mechanism and all this. This is the mechanism here, the same thing. Formaldehyde, the OH, you have 1 OH, that's your, guys here, that's your OR, correct? So the OR will come here, and then you have 2, this is already, and the H will come on this, so 2 OHs, that's the OR here. You assume that's your OR, so 1 OR and 1 OH, so that's hemiacetyl, correct? 1 OR, 1 OH, 1 OR, that's a hemiacetyl. Okay, guys, that's excellent. We have a couple minutes, and I think this chapter almost there. The last thing is Grignard reaction. Grignard reaction, I don't want you to memorize anything in it. If we can't finish it, we'll finish it later on. Grignard is about ketone or aldehyde, so you can make out of this an alcohol. So it goes from ketone or aldehyde, and you get reduction into back to alcohol. That's the whole idea is. That's what? A reduction. You are reducing the ketones or aldehyde into alcohol. That's using a Grignard reagent. A Grignard reagent is MgX, correct? O. So MgX R, not O, R. So alkyl magnesium halide, alkyl magnesium halide. This is Grignard, RMgX. When you add it to it, it will come to attach itself. You can see OMG, it cut itself from here. Mg will be acting on the oxygen here, and the R here, guys, the R will go where? The R will go to the MgX will be here, the R will come into X. So the R here on the carbon, the OMgX, the MgX on the oxygen. Then it will flip, you add H2O, then you get an alcohol. You get an alcohol out of it, and then magnesium halide. Are you following me here? So that's the way we can get a reduction of ketones and aldehyde using Grignard reagents. So that's, again, I'm not asking the mechanism, because the reaction itself in the lab is nicer, smoother, but sensitive for any moisture. When you start with this reaction in the lab, you have all the glassware you are using has to be dry in the oven before you start. Otherwise, 1 drop of H2O will hydrolyze the whole molecule. So it goes reverse. So here it is, it goes reverse. Here the reaction goes reverse. So I don't want you to memorize this aldehyde or ketones with this Grignard reagent. You get this intermediate, complex, and then you get up to secondary alcohol, correct? So that will be the chapter, that's it. No memorization of mechanism. I'm not asking any mechanism. Okay, thank you very much. Okay. What's that? You see here? Yeah, I think that's all it, and you can, that's a mechanism. We are not doing any mechanism. So just look at this.